Okay, so welcome to the final talk of the day. So we'll have Alex Youcis tell us about the Syntomic perspective on integral canonical.
Thank you very much, and thank you very much for the organizers for giving me the opportunity to speak here. So yeah, I want to tell you a little bit about some recent progress on integral canonical models of Shimura varieties. Everything I'll be doing is either joint with Naoki Imai and Imai Kato, I'll just write IKY for short, or with Kirti Madapusi, and I'll just write M. Okay, so I want to sort of tell you about new cases where you can sort of understand integral canonical models in maybe a more refined way. But I want to sort of start by talking about the more classical way. So I want to review a situation, but maybe write it in a way that's more conducive to what we're going to try to do for other Shimura varieties. So let me fix some notation that I hope won't be too offensive to anybody. So let's let p greater than 2 be a prime. I'm going to write non-script AG over QP sitting inside script AG over ZP for moduli of d-dimensional principally polarized abelian varieties. And then finally, I'm going to write this funny looking thing, which I sort of had to make up notation for. Hopefully this is not terrible. It's sort of terrible. So it's BTP because it's going to be p-divisible groups or Barsati-Tate groups. I'm going to put a PP up here so that you know that it's principally polarized. And I'm going to put 2G to indicate the height. So these are moduli of height 2G, principally polarized p-divisible groups. Okay. So in some sense, the entire talk is going to be trying to analogize the following picture. And I want to look at this picture a little bit more carefully. So what picture is that? It's the relationship between these two objects insofar as their integral powers. So more precisely, what we can do is the following thing. So we can start out on the generic fiber, so working over QP. And there's a way of mapping AG over to the classifying stack of GSP2G ZP, thought about as a profinite group. And this is just the Tate module. This is just saying that since we have a principal polarization, we not just get a Galois representation, but something valued in here. And maybe a fact that's either obvious or not obvious, depending on how much you thought about it before, is this gadget here is just the generic fiber of this moduli space of p-divisible loops. So I'm thinking about this as, for example, a stack over ZP, and when we pass to QP, we just get back this classifying stack. So now, both of these objects, from what I just told you, have natural integral models. Over here, it's just the moduli principally polarized abelian varieties, but now thinking over ZP. And over here is the genuine p-divisible set. And the thing is that this map, TP, actually lifts. Specifically, there's a map here. So I'm going to call it pi, in which case this Tate module thing is just the generic fiber. And what does it do? It just takes the p infinity torsion and a principally polarized abelian variety and gets out a principally polarized p-divisible. And it's a famous theorem of Serre-Tate that this is in fact p-adically formally a tall. Okay? So this is the picture I'm going to want to try to generalize for other Shimura varieties, but I want to tell you why it's a picture that's worth generalizing. It's only called the star. And I want to try to convince you of this by writing down the following theorem. That even though they may not have stated it this way, these two people. So this is a theorem of Grothendieck and Vazu, which says the following thing. Let's say I take X over ZP, let's say flat and normal. And let me write non-script X for its generic fiber. Okay. Then I can think about the following mapping question. So if I start out with a map to my moduli of abelian varieties over QP, I can ask the following question. Well, both of these have models. And I can ask, does this extend to the models? Right? But using this picture, I can formulate a slightly different question. Namely, what I can do is I can take this map that I was calling pi eta, which maps to this classifying stack for the general symplectic group. This sits inside of its natural integral model. And here I have the model of the map pi. And you can ask, does this composition lift? And the theorem is that these two liftings are actually equivalent. So the model of the map to the moduli of abelian varieties exists if and only if the map to this model of this classifying stack given by p-divisible groups lifts. Okay? And so I won't try to give a full proof of this, but maybe I'll give the briefest of sort of verbal sketches. So where does normality come into play? By some sort of maximum principle, if you want to show that this map from X to AG lifts up here, it suffices to show that each of the residue disks extends to a map here. Okay? These residue disks are exactly the same for these two things. That's what p-adic formal autonomous gives you. And since you have them lift here, you can pull it back. You should be a little unconvinced by that proof because all I've used is formal autonomous. And what the secret ingredient that's missing to just saying somehow, oh, well, that you can extend on these residue disks is you need Tate's theorem that somehow the Tate module functor is fully faithful if you start with normal input. So in fact, the map that takes an X here and spits out the generic thing is actually fully faithful if you start with normal input. That's the theorem of Tate. But that's roughly how you can prove this theorem. Are there any questions about that?
Can I have a very pedestrian question?
Please, please.
So what category are we in? So like you have schemes on the left-hand side.
Yeah.
And then on the right-hand side, what sort of objects are those?
So each of these are just pro-Artin stacks.
Pro-Artin.
Yeah, so if you truncate your p-divisible group, you get an honest Artin stack, and it's just the limit over the truncations. Similarly here, of course, you should really think about this as some sort of limit where you quotient out by z mod p to p at the end.
Okay.
Okay. So I think this is a sort of remarkable theorem because what it sort of tells you is that even though this is classifying truly global objects, I mean, I'm a little hesitant to say z-motives, but let's say something like z-motives. What this theorem somehow tells you is the delta, the difference between the generic fiber and the integral model, is entirely controlled by just at p data, which is perhaps a little surprising when you first look at it. Another question you might ask is, okay, this tells me how to characterize my model. I can tell you how to map into it just using at p data. But why would you ever want to do that? Because we already have a perfectly fine moduli space. And the answer is that that perfectly fine moduli space is using the fact that we have moduli descriptions of these things. And for more general Shimura varieties, we just simply don't. But the sort of new innovation that you're going to see here is we now do have good analogs of these. And because of a picture like this, that's enough to really get a handle on the integral models. Okay, so there's a lot of things you can do if you have this set up for a Shimura variety, and I'll tell you about them near the end of the talk. But I just want to give one more example that shows the power of this, because you might think, well, this gives some sort of at-p characterization of the model, but you maybe can't use it to do anything. But let me give one example of a fact that I think is quite neat. So as far as I could tell, I did some research, and it wasn't totally evident, but I think this is originally a theorem of Ort that was unpublished. And what this theorem says is that I can look at this moduli space of principally polarized abelian groups, and I can look at the map that I get to these principally polarized p-divisible groups of height 2g, and I can reduce this map modulo p. Okay? And what the theorem says is that this is a surjection, which in fact is in some sense quite surprising. What it's really saying is that you can take something purely at p that only has p infinity torsion, something like a ZP motive, and at least over FP at the level of points, you can always somehow promote it to something that has torsion away from P as well, to something like a global or an algebraic object. So the way that Ort proved this, at least as far as I could tell, was a pretty hard, meaning hard versus soft approach. But let me tell you, approach is actually is quite soft and generalizes. So here's a proof. Of course, I'm only going to sketch it. The first thing to notice is the following thing. This map, pi 0, the reduction modulo p of pi, is formally a tall. As we said, this is a famous theorem of certainty. And what does that imply? It implies that this map is open. Right? But also what's true is this map pi 0 is in fact partially proper. It satisfies the valuative criterion for properness. This is a theorem of de Jong. What is the content of this theorem? It says something like if you have an equicharacteristic P DVR and an abelian variety over the generic fiber, it lifts to an abelian variety over that DVR if and only if its P divisible group does. And what does this imply? It implies this map is closed, or at least specializing. And then finally, this stack is connected. And that's the proof. So it's sort of a quick proof of this fact that uses sort of this very soft general machinery. And that soft general machinery is quite useful because the way that you try to prove this by a hands-on approach is quite difficult in more general situations where you don't have a modular description of this object. Okay. Are there any questions about this? So our goal today, in some sense, is to describe how you can make sense of this picture for any Shimura variety. And as we said, the main issue is that we do not have a modular problem. So everyone's favorite part of a Shimura variety talk is where you spend 7 minutes writing down the notation, which is why I chose not to do that. So let me just point out some key features here, and then you can just peek over at any time if you want to see anything more precise. I'm going to be working in a Shimura variety, and I'm going to be fixing script G to be a reductive model of it over ZP. And my level at P is always going to be that hyperspecial subgroup. So I'm somehow only working in good reduction right now. Okay? The other thing is that I'm going to have this mu that pops up again and again and again, and this is just the integral model of the Hodge cocharacter. Okay? Everything else you can sort of glance over, but that's sort of the main gist. Okay. And please feel free to interrupt me at any time if you have questions. So again, we're going to try to generalize this picture, and we're going to do this in a sort of step-by-step process. So we want to get everything that occurs in this picture here, and in some sense, maybe a priori, all we start with is the Shimura variety, which is the thing down here. And just to say, I'm always just going to write SHK for the Shimura variety. I'm not going to worry about the GX. I'm not going to worry about the base change. So in some sense, this is our SHK. And at least at first glance, this is the only part of the picture that's immediately clear how to generalize. But the easiest second part is this map here, and this is something we can write down quite easily. The analog of this tape module. Okay, so how do we write down the analog of this for general Shimura variety? So a Shimura variety, in some sense, doesn't have a lot of structure when you first glance at it in an arithmetic situation. But one thing you can always get a handle on is the following thing. Your Shimura variety always comes in a family where you're allowed to vary the level. Okay? And in particular, what you're always free to do is we're starting at a level where the level at P is this G of CP, and you're allowed to let that level shrink to 0. So what I can do is I can take the limit is my KP shrinks to 0 of these various different level Shimura varieties, and this is a GCP bundle. Right, because somehow the Galois group of this thing, for experts in the audience, I'm assuming G is cuspidal. You can get around that, but with more notation, so let's ignore that. But the point is that the Galois group of this cover is something like G of CP mod KP. And so as you let KP shrink to 0, you're really just getting a bundle for G of CP. And what does this do? If you build a bundle for G of ZP, it in particular builds for you a map from your Shimura variety to the classifying step for G of ZP. Okay? So this part in some sense is easy. And it's an exercise to check if you've never seen this before, that the tape module really is just letting the level of the Siegel-type Shimura variety pass to 0. So this is exactly just the analog of the tape module in the Siegel case. So This one's maybe not so difficult to generalize, but now we have three more things to do. We need to build the model. We need to build the model of B of GZP. And we need to lift the model that we just constructed. We need to model the map that we just constructed between those models of the individual spaces. And all three of those things are very hard. Okay? So what is the fundamental difficulty? So if you want to try to extend this theory beyond, for example, the PEL type case, or even really beyond the Ziegler case, you run into the following issue. So the principal polarization had something to do with the fact that the Shimura variety was a GSP2G Shimura variety. For a more general Shimura variety, G may be of Hodge type. You'd want to say that what should go here are p-divisible groups with G structure, right? That's naturally what you'd want to do. But there's a real serious issue with that, which is that G structure is a linear algebra construction that requires you to be able to do linear algebra with p-divisible groups. And I don't know what the tensor product of two p-divisible groups is. I don't know what various linear algebra constructions are. And so the issue is that G structure is not actually something that makes sense directly on the p-divisible group. So we really kind of need to change perspectives to generalize this part of the picture. And this is in some sense the part that requires the heaviest machinery from recent years. Okay, so what I want to do now is I want to tell you what the analog is of principally polarized p-divisible groups. And the answer was originally suggested in a short article by Drinfeld, which I feel compelled to point this out because this is one of my favorite turns of phrase. So Drinfeld believed, sort of independently, lots of people working on this thing, but he was thinking about pictures like this, and he believed in what he called a principle of Shimurian democracy, and said that all Shimura varieties should be treated equal. The Ziegler case or the PEL type case should not be given special treatment. All of this should work for all Shimura varieties. And him trying to define the analog of these p-divisible groups of G structure was part of this principle of Shimurian democracy, which I really like. So it was suggested in this article by Drinfeld, and it was really studied seriously by Zachary Gardner and Kirti Madapusi. Okay? So what is this? This is going to be the most exotic object of the talk, so I'll try to give some idea of what this thing actually looks like. So it's going to be some sort of functor. So we have the G and the mu, where G was our reductive model and mu is the Hodge co-character. Unsurprisingly, to recover this case, we're going to take the general symplectic group and the co-character of G1s and G0s. And what does it do? It sends X over W, a p-adic formal scheme. And you can, in fact, upgrade it to put in essentially any input you want. And then sort of being able to put in animated inputs is actually important for some of the proofs, but not so much for the things that we're going to be talking about today. And it spits out the following gadgets. It spits out G bundles on X sin type mu. Okay, so G bundles is maybe not so scary. Type mu is kind of the standard thing where there's some sort of relative position going on. The thing that maybe is the most daunting in some sense from a technical perspective is this X sin. So I won't tell you what X sin is precisely. I'd be happy to talk about it after the talk, or Bargov is here. And this is an object that was created both by Drinfeld and Bott-Flory. And it's what's called the syntomification of X. Okay? So I'll give an example in a second of what type of object this looks like, or at least in some cases how you can think about this thing. But I want to just give an analogy to the sort of Hodge theory crowd that at least to me is somewhat compelling. And it's not a perfect analogy, but I think it's a good one. So you can sort of think about this as a p-adic or relative version of the twistor P1. So if you've not seen the twistor P1 before, this is the non-trivial Brouwer severity variety over R. And it has the interesting feature that vector bundles on it are exactly Hodge structures over R. And so G bundles on it are exactly Hodge structures over R with G structure. And somehow this X sin is supposed to be doing something similar. It's a geometric object whose bundles somehow encode something like mixed Hodge modules over X. That's the idea. But this is in some sense quite difficult to picture. And to really get the most out of this, you sort of need to use this in very complicated situations where, for example, this stack doesn't even have to be a classical stack, but it surfaces back to reality occasionally. And often you can actually prove things by dealing with those cases where it's closer to something more reasonable. So let me give an example. So let me start with E over FP bar, a supersingular elliptic curve. Okay? Then what I can always do is I can look at its universal deformation. Okay, and this lives over ZP brev of T. ZP brev is just W of FP bar. And so it turns out that there is a version of Dieudonné theory that somehow works in the Syntomic realm. And maybe that's not so surprising because somehow if we're trying to classify p-divisible groups, we want some sort of Tanakian analog of Dieudonné theory. And that's something that you can do here. And you can sort of concretely understand what these things look like in this case. So for instance, what you can do is take the Syntomic Dieudonné module of this thing. What this is precisely is this stack that you build out of X as functorial. And in particular, you can push forward down to the syntomification of this thing, the structure sheaf on the syntomification of E. And this feels completely unhelpful because I haven't said anything that's tractable a priori. But the key thing, and this is how a lot of the proofs go, is that this data is equivalent to something much more down to earth. Namely, this data is equivalent to, you look at the power series ring in two variables, you look at the free rank 2 module over it, and you act on this by a Frobenius that looks like this. I think I did not screw up the matrices. Okay? So somehow the beautiful thing is that in reasonable cases, all of the Syntomic doodads kind of reduce down to more classical Dieudonné theory or crystalline theory or something that you can really kind of get your hands on. But it works completely well over any base. And so often when you try to prove things about these, you maybe try to restrict to the case where X is smooth. And there you can sort of get a much more concrete handle on what these things look like. Okay? Any questions? So it is true, I think, that these things are quite daunting at first, but they're very powerful. That's why a lot of this machinery took such a long time to build. But they're not hopelessly complicated. And one thing I'd like to point out is this is the case for elliptic curves. This is the modular curve case. We already knew what the modular problem was in the modular curve case. But you can plug E7 into here, and you can get a similar description. It will just require 56 by 56 matrices. So this is not specific to GL2, which is what the somehow elliptic curve case is. It's just that the matrices there are small. But you can do this actually for any group. You can write down matrices locally that somehow describe what these things are.
So how should we think of the variable U there? Like what is that what syntomicness is adding? Is the U?
So sort of. Like what you should think about, I don't know if this is going to be helpful, but forget Syntomic for a second. And let's think about this thing prismatization, which is morally they're like roughly the same thing. This is some complicated stack, but it has a natural cover by the Breuil-Kissen prism, which is just ZP double brackets U. So somehow you should think about this U thing is somehow local coordinates for the syntomification. All this Breuil-Kissen theory, all those things are somehow local coordinates of what's happening.
Okay.
So this arrow is hiding a lot because this is a cover, and a priori you have to descend the data along the cover. There's a non-trivial theorem that says it automatically descends in this case, which is why I'm hiding some information here.
But so you aren't telling us what it is, you're justifying that
What is an equivalent piece of data?
It works to
Exactly.
Okay.
And so when you want to manipulate these things in practice, you somehow reduce these local coordinates and you can do calculations there, and that's often enough to get what you need. Okay. Any other questions? Okay, so a priori, I just wrote down for you some functor. And you might think, well, this functor is pretty gnarly. In particular, it seems hard to imagine doing geometric arguments involving this functor. But then you look back to what we're trying to analogize. And you can think to the question that Jacob asked me, which is what sort of object is this moduli space of p-divisible groups? And I said it's a pro-smooth Artin stack. So it turns out in general that these things have that kind of structure. The theorem so the much harder version of this is the first one, which is due to Kirti Madapusi and his student Zachary Gardner, which is that this gadget, this functor, is a pro-smooth formal Artin stack. Which, I mean, at first that might sound like we're venturing into some realm of no hope, but it's actually not so bad. We make geometric arguments about p-divisible groups quite often, and if you're very careful about them, it's not really an algebraic stack. It's only somehow, when you truncate to each level, is it algebraic? And the same sort of thing is happening here. And it turns out that for many arguments, that's enough geometric structure to get what you want.
Sorry, can I ask why this thing, the special fiber is what we want to do?
What is what you want it to be?
This object you constructed, over the special fiber you want it to be BGCP. BG. This is supposed to be a model over the generic fiber.
So you're asking a great question. Let me finish this bullet and then see if it answers your question. So one thing that Kirti and I did in our paper is we proved that there exists an algebrization you can call BTGU Hodge infinity, which is a pro-smooth Artin stack. So basically, this thing was formal, and we somehow naturally algebraized it, and it has generic fiber. BGZ. To answer your question, it's like similar to the fact that if you formally complete p-divisible groups as a stack and you take the generic fiber, you're picking up some sort of crystalline things, but the generic fiber as a stack is just local systems. So you can algebraize this. And once you algebraize this, what I'm saying is that this is somehow the correct analog of this right column of the picture. Okay. Please.
In principle, I also have just my crystalline DNF module, I have the Gauss-Wannian connection. Are you saying that it's recoverable from this Frobenius, or it's supposed to be another?
No. So it's exactly the same as in Falting's very ramified paper. What he proves is that there's a unique connection that's F horizontal, right? In this case. And so when he describes the deformation of p-divisible groups with like Fontaine-Phi theory, he doesn't tell you what the connection is, he just says there is one, right? Similarly, there's a descent data here, and what I'm sweeping under the rug is that descent data is unique. I'm not telling you what it is, just like I'm not telling you what the connection is that Faltings does. But that's a great question. I'm hiding the descent data. But because it's an equivalence of categories, you can often still manipulate on this code. Any other questions?
So in the end, do you just get like, there's some explicit thing you can write down, which is like an analog of a p-divisible group, but for each sort of E7, E6.
That's exactly right. Yeah.
It's some like linear algebra type.
Exactly. Like somehow if you, so the thing is this, if you feed into this something like even the dual numbers over FP, this thing is quite gnarly. Okay. But if you feed in a smooth input, then they have these very sort of natural covers, which are much more understandable. And for example, for E7, you'll get a description as some sort of module with Frobenius and tensors. It's just, again, it will be like 56 by 56 at least.
Did you write it down?
Yes, you can write it down.
But did you?
Did I write it down? Absolutely not. I know where it's written down, but I didn't write it down.
It is written down.
define written down. In principle, is there an algorithm? Yes. Did someone actually do it and write out the large matrices? No, I don't think so. But you could. Actually, that would be an interesting thing to have a student do. Just no, I mean it's very explicit. It really just comes down mostly to the sort of representation theory of V7. It has nothing to do with chaotic Hodge theory. Okay. So this is the analog somehow of the right column. And we come to what is in some sense the crux of the whole thing, which is this gave us the analog of this bottom row here. This algebraization of this BTG mu gives us the analog of the right column. What we're missing is the top left, the model of the Shimura variety, and the map to this BTG mu alge. Okay? And in some sense, I'm sort of slow rolling the fact that historically people didn't care about this a priori, right? What they really cared about was integral models of Shimura varieties. And somehow this is really the prize, is the integral model of the Shimura variety. And it's exactly the part of the picture I haven't told you about. So I want to tell you how to fill it in. Okay. So there is a long history of definitions of integral canonical models of Shimura varieties. Because again, maybe the thing I should point out is that if you're very used to the Siegel case, it seems like there shouldn't be much choice, right? Because when you have this model here, what model do you take? You take the same model with the same moduli problem. These don't have moduli problems. So what do? And so it was a long-standing problem, going back to Langlands' first article about Langlands, that he was trying to think about integral models of Shimura varieties and trying to write down what the good canonical notion of model should be. And there's a long history of trying to define these in many different ways and study them in many different ways. And so I want to tell you about the sort of new way that involves this diagram. Okay, so we'll do exactly what I just said, which is we're going to try to understand this object in this map is a definition, and then I'll have to tell you is a theorem that actually exists in some cases. Okay, so definition. The sort of primitive version of this appeared in my paper with Hiroki and Naoki, and then the version I'm going to tell you here appears in my paper with Kirthi. So, definition, a separated finite type model, SK, of our Shimura variety is a Syntomic integral canonical model. If almost by definition, you'll see we have that top row, but there's going to be an extra little bit that we have to fill in. So the first thing is that there is a formally atoll map. I should say p-adically formally atoll. Pi from this model to this stack that was constructed there, BTG mu alge infinity, modeling the map that we wrote down right there. So the map from SHK to this classified stack. And you can prove that in this case such a model is unique, but so you just need there exists. Okay. I should say probably, yeah. No, such a model of exists is unique. So as far as this picture is concerned, I've somehow defined the top row into existence, but that's actually not enough to characterize it. What you really need is something more. What you really need is the following thing. If you take the completion of this model and you look at the generic fiber, this is some rigid analytic subset of the Shimura variety. And which rigid analytic subset is it? It's the crystalline locus of this map pi eta. So this pi eta, whatever it is, it's just picking out some family of ZP local systems on your Shimura variety. And I'm asking that the generic fiber of the completion is exactly those points where those family of local systems are all crystalline. You can take one faithful representation. You don't have to worry about all local systems at the same time. So this is the definition. So it's almost just that we have that top row from star filling in the picture, but we require this extra little bit, and this extra little bit's quite important. Okay. So there's one more thing that we need, an extra condition. So we need a property of a Syntomic integral canonical model. So as we'll see in a second, these are unique if they exist. And so what I'm about to tell you is a property of that model that should be true always, but we can't prove it. So we're currently putting it as a condition. So SK is, get ready for this fun word, limpid if every point of this crystalline locus is L unramified for every L not equal to P. So just like you somehow make GZP local systems, you can make ZL local systems for every L not equal to P, and I want them to be unramified. And in some sense, I'll come back to this in a second. So Baker, Shankar, Zimmerman have a notion of models that they study, and largely they somehow focus on the L not equals P picture. In this original article of myself with Hiroki Naoki, we somehow only focus on this P picture, but unsurprisingly, really you should consider both at the same time. Okay.
Just so I'm not confused, why can't you take like did you say that it's unique? So what if you take like an open subscheme of one of these models? What stops you from the other one?
That's because the generic fiber is fixed.
Yeah.
And saying what this is really fixes the special fiber because you can surject by specialization.
Just remind me what this is, because I'm confused.
It's, you take the, so in fact, I was going to draw this picture later, but let me just draw it now. So there's sort of a general philosophy that you can picture. Your Shimura variety lives over here. Every model looks like this, right? It looks like, so you know this. It looks like something like you take a bridge analytic open, you glue to it a formal scheme, right? So for people that don't know, this is the completions generic fiber. This is the model special fiber. I thought about trying to write this in chalk. I aspire to do what Phil does with chalk, but I can't color chalk, but maybe I'll just do this. It's a first thing. So this is the specialization map. And kind of this is the thing that stops the special fiber from being too small. Okay. Okay, great. So this is a definition, but a priori, there's nothing that satisfies this definition. So what I need to tell you now is that, in fact, there's an abundancy of these models. Okay? So theorem. Limpid integral canonical models exist if GX is, so the first one is abelian-type. Okay, so this is the regime that was studied by many people. Lastly, and sort of the most strongest results by Mark Kissin. And I'll say a little bit on what the relationship to Kissin's models are in a second. But also Kim Madapusi when P equals 2. Okay. Pre-abelian type as long as P is greater than 2. And finally, arbitrary as long as P is sufficiently large. And this is the regime studied by Baker, Shankar. Okay, so essentially, every time some notion of integral canonical model was known to exist, we're now saying that one of these limpid integral canonical models exists. But there's one funny thing. So I didn't state who this model is due to? And the answer is because we actually construct these models. So in fact, and here comes the dramatic flourish. So I've also written another thing. So here's a fun thing you can prove about these limpid ICMs. They're automatically inherited by closed sub-Shimura varieties, but they also ascend and descend along central covers. Okay? So you start with AG and you prove this is limpid. What does this correspond to? It's Sertate. That's what gives you this part here. It's Coleman I Vita. That's what gives you this part here. And it's Naranok Shafarevich. That's what gives you this part here. Okay? So you know that this thing's limpid. Hodge are by definition closed. So they immediately go. Hodge cover by central covers abelian type. So they descend. And pre-abelian type map by central covers. So it ascends. And so in fact, we sort of reconstruct Kissin's models. So when Kissin passes from Hodge to abelian type, he does an integral analog of Deline's yoga about connected components. And it's quite delicate. It's something that I've used many times. And it's quite an involved process. But in fact, here, you can sort of drop in AG, and it just goes along a conveyor belt and spits out pre-abelian type. And the point is, these stacks have enough geometry that you can use their geometry to move between these different Shimura varieties. Somehow this stack is what's giving you the extra geometry that you need. And that's why it's hard for L not equals P to prove these type of results, because they don't have as much geometry in the p-adic situation. So in fact, this proves Kissin's theory sort of in maybe a more streamlined way. And because it's more streamlined, can also deal with this pre-abelian type, which if you're curious are just a couple more type D cases. Okay. So let's see what's next.
In the general, the arbitrary case,
Yes.
I'm guessing the answer is you do the same thing. We just take some model and then wait for it to be smooth and all that stuff.
So what I'd say is the input from BST in some sense. So what you guys do is you take the models essentially from the Andre Ort paper and you develop a whole bunch of geometry and you study them, right? We essentially do the same thing. We take the Andre Ort models and we prove they have these properties.
But so when you say the Android model, you just mean you take some model.
Some models
like
fit
a big enough prime where things are good. Okay.
Yeah. And it's possible. I don't want to promise this, but it's possible that technically you could require this to be ever so slightly smaller, but they're both so big that it's not clear
I see.
that distinction matters. Yeah.
So what are the properties you need? You need crystallinity, you need Cordella Spencer being big in some sense.
Yeah. I mean, and the other thing you need is a log F isocrystal.
But that Canonical versioning would give that, right?
Yeah.
Okay.
So I should say that, I mean, and this is what they're saying, and I'm confirming this is true. What we're doing here is nothing really super different than Baker, Shankar, Zimmerman. We're essentially taking the same models that they consider with some of the same properties they use and showing that you can get this from that. The only new construction, I would say, in some sense, is more in the sort of pre-abelian type setting. Okay.
Is there a hope? Oh, sorry, not the last question, I promise. Is there a hope to get the lower primes with this kind of approach?
Maybe, but maybe we can talk about that some other time. But yes, maybe there's a hope. Okay. So where am I? Okay, so now I think there's a very important question that we have to answer. Okay. And that question is the following. What do we get? So when I was talking and Kirti was talking about these models, some other people, we definitely got the feeling there was a bit of model fatigue. Because as I said, this definition is, there was Milne's definition, there was IKY's definition, there's BST's definition, now there's this definition. So what do we get? Why is this worth considering? And the answer is, it seems like this is exactly the information you need to get most things you want to understand about the model. So let me state the things that we sort of talked about at the beginning. So the first thing is that it has a mapping property just like in the case of abelian varieties. So if we start with x over zp, let's say flat normal. And let me write x for its generic fiber. Then if I start with a map to the generic fiber of my Shimura variety, this lifts. I've come to recently realize that maybe lifts is a weird word here, but I mean lifts to the integral level to SK. And all you need here, by the way, is that this is a Syntomic integral canonical model. This theorem doesn't need limpid, which is why it's uniquely characterizing it. Even that's why limpid's a property. If and only if the induced map to B of GCP lifts to this BTG mu. Okay. The other thing that I find very pleasant, at least from, I really like this Bobo-Laszlo gluing picture, so I'm going to say about something more about that in a second. But the second thing is, if you look at the completion, so this is now a formal scheme. This is a Neron model of its generic fiber. Meaning that if you have any smooth formal scheme and a map generically, it automatically lifts. Okay? So what that tells you is a very interesting thing over here that's possibly completely useless, but I think it's quite interesting. So you saw that one way to think about the model is you take the Shimura variety, you look at some rigid analytic subset, and you glue to it a formal scheme. Okay? What this theorem is telling you is this. If U is the crystalline locus, that's this rigid analytic subset here. And script U is its Neron model. Then combining these results, you see that S is just the result of taking the Shimura variety and gluing along the crystalline locus its Neron model. So in theory, we can, I mean, this is not useful, it's mostly a joke, but in theory, you know how to construct an integral model for any prime. Just prove there's a crystalline locus and prove there's a Neron model. But unsurprisingly, that's almost impossible to deal with because Neron models are very hard to prove they exist, especially in these sort of geometric situations. But in theory, it could be a useful way of doing these things. So that's one thing that you get.
I'll like to put it that possible strategy. What was the locus to begin with? Was there any a rigid space or just a collection of points?
So you're asking one of the key questions. As far as I know, it's an open question about whether given a variety over QP, there's a, let's say, quasi-compact, retro-compact, rigid analytic open, whose classical points are exactly the crystalline points. As far as I know, that's open. Using results of Shimizu and results of Kedlaya, you can say something about spreading out and getting some sort of openness, but it's hard to pin down that it's not like too big or too small, or somehow it's hard to, with their work, figure out whether like a type 5 point should be in there. Okay. So the second thing that you can get is the generalization of the result of Oort that I mentioned before. So I'm going to state it like this. For all known limpid ICMs, meaning the ones that are up here, because, so let me just sort of not bury the lead. We prove what I'm about to say with an extra assumption, and we can verify that assumption in all known cases. It's probably true in general. But let me just say for these, without, so I don't have to say the extra condition. The map from the special fiber of the Shimura variety to BTG mu alg infinity tensor FP is surjective. So it's some sort of algebraization or globalization question. Somehow it says if you have an E7 motive over FP bar of a certain type, then you can always find some sort of E7 motive over Z that completes it. Okay. So I want to mention some other things that you can get out of these integral canonical models. But before I do, are there any questions? Yes, please.
If you take 2 points on the right-hand side, which say are like, let's say isosceles points, and you look at the fibers in the Shimura varieties.
Yeah.
You guys also show that there's like a p-pi Hecke operator going from one fiber to the other.
Let me think about that. I think maybe, but let me think about that before I answer quickly. I mean, I should mention that I think similar to what happens in BST, if you add these limpet things, you automatically get prime to p Hecke correspondences. You get a lot of the same setup that happens in this BST paper. But let me mention some other things that you can do with these models.
Alex,
Yeah.
I didn't catch what you said about the uniqueness, but is it right that the first part of the left theorem proves that they're unique if they exist? Or
The one does?
yeah.
Yeah, because I mean this stack is pro smooth, and so you automatically get the S is smooth, and so the fact that you get normal inputs. I mean, this also proves it's unique, I guess, but okay. So what are some other things that you can do with this? So some of these are also obtained by BST, but maybe in a slightly different format or a different way. But so let me say one example of this. You can get Serre coordinates. And you can get canonical lists for ordinary points. Maybe I should have said that backwards, but and you can even sort of prove that you have this analog of a cascade in the sense of Monin. You can prove that the deformation theory of these things looks like an iterated formal p-divisible group, which is what I mean by the Serre coordinates thing. But in some sense, I would say, I mean, I really like Koch theory and Shimura varieties, but I would say that one of my main motivations for Shimura varieties comes from the Langlands program. And there's some import there. So one thing that you can get from this is a Youcis text in the sense of Zhang and Peter Schulze. So this is a result of seeing Li here from Madapusi. And maybe I won't go too heavily into what a Youcis text means, but somehow the point is that you can actually define a good notion of p isogeny over BTG mu just on that side, and by pulling it back, you get a good notion of p isogeny here. Okay, so this already seems promising. There was an AIM conference last week about some of these ideas, and it seems like maybe this could already be useful for trying to prove some new compatibilities of Fark-Schulze with some global questions and Langlands. One of the ones that I'm quite excited about is that it seems like you can prove Langlands-Rappaport type parameterizations of points. Parameterizations of points. This is also in this, I think, forthcoming work of Seeing and Kirthi. So for people that haven't seen this before, maybe I can sort of briefly say that the reason that Langlands himself was originally interested in these integral canonical models, as I sort of hinted, is that he thought that doing a kind of Lefschetz type point counting on the special fiber would produce formulae that would help you somehow pin down the Langlands correspondence in the cohomology of Shimura varieties. And the precise version of what those kind of decompositions needed to do these point counting are what's called this Langlands-Rappaport conjecture. And it seems like this definition of the model is somehow enough to really let you get a handle on even things like this. So instead of maybe saying some more things that this thing can do, I'd be happy to talk to you afterwards if you're curious about what they are. Let me mention what you could try to do in the future. So there's maybe some ideas here, but they're definitely far from completion. So I just want to mention it as like a possible thing to think about. So you could try to create versions of this for toroidal compactifications. And what that would sort of require you to do is to build logarithmic versions of these things. And I think there's already a decent idea of how to do that. But maybe let me just say that the reason why that's somewhat tempting in sort of in a tangential way to Jacob's question is it seems like building models of these compactifications is easier than building models themselves, partly because you don't have to worry about this crystalline locus condition. Somehow for the compactification, all the points should be semi-stable. So you shouldn't have to be kind of like picking out some locus inside of there. And so somehow creating versions of this that works with the compactifications could be quite helpful to try to remove these conditions on P. Okay, so let me maybe just stop there.
Okay, any questions?
So I guess over this diagram, if you try to, can you do something with the period image case, but it won't be formally a tell anymore, but.
So this is a great question. I'm actually very glad you asked this. So what I would say is that I think that this approach to models in some sense maybe has more robust conclusions than what shows up in Baker, Shangar, Zimmerman because we somehow consider at P. But somehow key to doing a lot of these things is that, where did I write it somewhere? This thing has good geometry. And somehow in the minuscule case, that's true. Outside of the minuscule case, this thing will only maybe exist as some analytic stack or something. And so somehow a lot of the structure comes from this having reasonable geometry. I think outside of the minuscule range, or maybe even just outside of the Shimura variety range, it's not clear, at least for now, how to somehow make this fit into the picture. It's a really good question, but somehow I think that this is really kind of tailor-made to understand specifically the minuscule Shimura variety type situation. I should also mention, I guess I didn't emphasize this, that these stacks, all of their things have nothing to do with Shimura varieties. They're purely local, as you saw, and they don't require G mu to come from a Shimura variety. Somehow in the notation I set that up, but it has nothing to do with that. You can take E8 here if you want.
Other questions?
Could you briefly explain the proof of algebraization?
Yeah, so the proof is kind of maybe what you expect. So it's a Vogel-Laszlo gluing. So what we essentially do is we define BTG mu alg of R is something like BGZP of R1 over P cross BTG mu of R hat over B of GZP R hat 1 over P. And then we do some sort of Arden-Lawyer representability to check that this works. In theory, so one thing I should mention is that this Vogel-Laszlo gluing sort of always exists in the realm of algebraic spaces. You can take any algebraic space, any formal algebraic space, and glue something to it and get an algebraic space. We don't know that for stacks. If we did, we could just do that. So we have to prove this more by hand. But that's the rough idea. Is that okay, Mingzer? Okay. Yeah.
So you said that you can make your BTG mu even after the Shimura case, but just to confirm, do you need mu to be minuscule?
Oh, yeah. I mean, you can make a definition of mu's not minuscule, but I think maybe here's like an analog. Like if you look at moduli space of Stukas, right? If mu is minuscule, you get a rigid space. If you don't, you get a diamond. It's like a similar thing. I think for this to have classical geometry, you need mu to be minuscule. So you could try to define something, but it won't be a reasonable geometric object, at least in a classical sense.
Any other questions? Okay, so let's